when we get to the bottom of a black hole, we're going to try to rewrite this as topological relativity. And we're going to need some loops here. So essentially, the electron comes through and it hits some impurities and it scatters, but you could have some charge buildup. So to me, this kind of seems like the impurity is like uh, just the point, which would be essentially the singularity of the black hole. So we should be able to define a friedel sum, not just for electrons, but for gravitons, gravitational waves. These phase shifts that occur when we scatter, they come from the shapes of the electron. So if we want to just consider just a regular old point-like shape or a spherical shape, we could go into the S shape, the very fundamental shape. So that brings me to sort of maybe this type of thinking where, when we have these black holes, they're made of these quasi-normal modes, quasi-normal modes. And they kind of look like this, but essentially they're like waves, gravitational waves, G waves. And so they're wrapping around this black hole, kind of like this. But if we were to look at topology, we can take a loop and we could slide that loop all the way down to the point where uh, it looks like it becomes a point, but it's really just the same loop, sort of in a different form. Um, so, we have to basically start with general relativity. So here it is. Here's the curvature. Um, Although we're applying the curvature on this spin connection here, which is a little angle sort of that we're putting. Well, we have to define this algebra here that we're sort of taking translations and translations and Lorentz boosts. So we move around and we can do it really fast in Lorentz form, so we can kind of spin around and do translations and stuff. So we have x, y, and we have t. So we have a triad right here. These are the one forms. So we have e to the alpha, and then there's the translations that we can do, so we can move around through these little coordinates. Okay. And then here we have the spin connection, so we're sort of doing these rotations, I suppose, and we're putting them onto the coordinates as well. And these are the Lorentz boosts. All right, so we can define curvature like this, and we can define torsion like this, in the sense that it doesn't fit, like, when you're trying to fit something together, it doesn't quite fit right. I don't know, that's kind of what torsion is. So we can set that equal to 0, essentially, and we can recover regular old general relativity. So we have this A. This is uh, the gauge that we have. It's just a one form, I guess. And we are essentially summing the torsion part and the curvature part. So this can sort of go away, and we could be left with just that if we want to. But so we have this gauge. So we put this gauge into the Chern-Simons integral because we just need to take gauge transformations uh, using sort of like changing with the same magnitude using those three coordinates there. We're going to take the three dimensions that we have, time, space, and, well, time, x, y, and z. And then we basically take some traces and we can recover the regular old Hilbert-Einstein action. This one right here. You might not be able to see the pointer, but it's this one right here. And, it's equal to essentially this. Once we take all these traces, it boils down to this. But it's rewritten in the language of our gauge. It's the same equation is rewritten in the language of our gauge. All right. Now, the reason we want to rewrite it in this language is because now we have a special gauge we can use that we can take a limit of as we go to the radius becomes 0. So we have these little loops. So we could take the polynomial of this gauge. The idea here is that once we get down to uh, sort of the bottom portion of this, How do we do? How do we get down to the bottom? Well, we have to take this loop and call it r theta, and then we have to take theta going from 0 to 2 pi minus a little deficit angle. And the reason we have that is because if you're trying to go around a circle in a curved space, it's not going to be 2 pi exactly. It'll be slightly less or slightly different. So we have a little deficit angle in our curved space. So we need that. And then all we got to do is basically set this radius thing to be able to go from 0 to 1. So now we kind of have this 0 to 2 pi minus delta and a 0 to 1 situation. We parameterized our coordinates now into this new system where we have this radius and this theta. So all we have to do is just reparameterize now r theta. We'll kind of designate this as a loop. And then, um, so then we have these 2 points that are important. So kind of like r is fully r at 1, and we have a theta there. Or at 0, when we have r equals 0, we technically have the singularity, but we have this theta popping up there. So, you know, we have to measure this angle that we get. So the singularity doesn't really exist. It's not a singularity. We're just like analyzing the coordinates at that point. All right. And so if we take this little limit and we go down to figure out what the angle is at that r equals 0, we find that it's just delta 0. So that's going to be the angle that we find at at the with the singularity. That's the deficit angle of going around the loop. So if you have empty space, then the limit as here, these are just limits as r goes to 0, and we have the holonomy of this loop group becomes I, which is just empty space, you know, just flat empty space. But if we have a mass loop, meaning there's an actual um, um, angle there, then it means that we have a mass. We can designate this mass over here. We can quantize these things in terms of n. So we have n loops at some particular point. But this all just comes from the very basic fundamental one at the 0 point. So we'll start there, and then we have to quantize it from there going upwards using n's. So it's a sum. Remember the friedel sum where we started with. But anyway, so essentially you can kind of see what it looks like. This is topological relativity, where you can just think of it like a map, where at any point on the map, it doesn't matter where you're standing, there's always a loop that's just, you're standing on a loop somewhere. Every single particle, everything's just on a loop, and you gotta loop it this way, sort of in a three-dimensional or four-dimensional space. This is sort of the Chern-Simons in the three-dimensional version, where you have to take two coordinates, consider their curvature as being sort of this gauge transformation here, and this is going to put in your 4 dimensions of space-time. There's the cosmological constant. Anyway, so what are we doing here? Remember that we have these masses that we can get from these loops, because these loops, they might have quantized masses. So it's g, m, some alpha. Don't really know what that constant would be. But essentially, we can see that at any point, we can measure the holonomy of that group, and we will get a phase angle. All right. If we integrate uh, this gauge over this a closed loop, then we're going to get a deficit angle. Remember, if we just go around this loop and we start and we end at the same point, you know, we might not have gone 2 pi. So that's essentially what this is measuring. It's measuring the integral around the loop. It's really important to sort of recognize that. So if we go around this loop, I don't know if I can draw this, but this is the key. We go around the loop. Let's say it's like more like a loop that looked like this or something. Well, there's not really 2 pi at this point. So there's a deficit angle. This is not equal to 2 pi, right? And so that's why we get this little angles. We do this little integral around this loop, and that gives us a mass. Um, it's going to require some scaling constant here. But most importantly, it quantizes uh it quantizes these angles. So we get specific angles out of this because we're subtracting from 2 pi, so we get some angle. The question is, what is the angle? Is it pi? Is it 2 pi? It's likely to just be pi. If it is, then we can quantize the spacetime using a friedel sum. So we can call some degeneracy. Doesn't really matter because if we go to degeneracy of the 0, then this just becomes 1 anyway. So this doesn't really matter until you start going up to further ends. But you have the 1 over pi from the friedel sum. And let's say that the angle was just equal to pi. And you'd get 1, so you'd get one space-time loop at the singularity, and that would be correct. Um, so this kind of quantizes the number of twists that you have at any particular point in space. But, you know, it's kind of interesting. But anyway, the idea is that this can quantize space-time without requiring extra dimensions. We don't need string theory, although the mathematics here is very similar. We mainly just need to think of this as topological, a topological map that has these loops. And once we get to the point of one of these loops, we are simply taking a deficit angle and we're sticking to the holonomy. We're taking the limit as the holonomy group reaches R0. And if we do that, again, we just get the deficit angle out of that. So um, I think this helps to get rid of the singularity that we have in black holes. And I think this explains, um, a lot of stuff. I think it's kind of interesting. Again, we started with the friedel sum. I'm just trying to figure out what it is. I have a lot of copies here. But that's what it is. It's kind of, we're just sort of getting a little charge buildup of um, of gravitons rather, or mass rather, or space something. I don't know what those things are. I think they're just gravitational waves there that we're just building up. Instead of electron waves, we're building up gravitational waves. I'm pretty sure that these are gravitational waves, quantized and gravitational waves that are wrapped around the black hole, and I think we can put them like that, because what else are you going to have in a black hole? They're gravitational waves. It's essentially a Friedel sum of gravitational waves inside the black hole. Anyway, hopefully this was enlightening. I know it's kind of 2 in the morning, but that's when the best ideas happen, and